inside the galaxy itself. On January 1st, 1990, from its orbit around Earth, the Goddard Space Flight Center's Cosmic Background Explorer captured this edge-on view of our Milky Way galaxy in infrared light. The galaxy has a center with a central bulge, a disk of rotating stars and dust, and a halo with lots of globular clusters. The disk is around 100,000 light years in diameter, and the halo is much larger than that. We'll go into each of these galaxy components, starting with the galactic center. Here we have one of the most detailed images of our galaxy ever created. It is constructed from over 1,000 photographs taken from the darkest places on Earth and painstakingly stitched together. We exist inside the galaxy, so we have to view it all around us as we rotate each day. As we look into the plane of the galaxy, we see that the stars are so closely packed together that it looks like a bright glow. We also see tremendous dust clouds obscuring most of the stars. As we look above and below the center line, the number of stars decreases to the point where they are readily seen as individual stars, and the dust clouds are gone. The world's great space observatories, the Hubble Space Telescope, the Spitzer Space Telescope, and the Chandra X-ray Observatory, have collaborated to produce this unprecedented look at the central region of our galaxy. Hubble documented vast arcs of gas heated by stellar winds from very large stars. Spitzer's infrared picked up the pervasive heat signals of all these stars. And Chandra detected X-ray sources from ultra-dense neutron stars and small black holes. Together they produced this spectacular image. The central object in the Milky Way is known as Sagittarius A star, or SAG-A star for short. It is surrounded by so many stars and gas and dust that it is almost impossible to see. Teams of astronomers have been working on understanding SAG-A star for over 20 years. The UCLA Galactic Center Group is one. In conjunction with the new Keck Observatory on top of the Mauna Kea volcano in Hawaii and the Max Planck Institute in Germany, they have made dramatic progress in advancing our understanding of this critically important part of our galaxy. By the turn of our new century, after years of careful observation, the speeds and trajectories for these stars were calculated. This enabled measuring the precise location of the point they are all orbiting around. But when we look at this point, we don't see anything. The measured orbits also identified the gravitational pull from this point, which in turn gave us its mass at 4 million times the Sun's mass. This was strong evidence that SAG-A star was a black hole because stars are known to be unstable at much smaller masses. Further observations of the star S2 showed that its orbit takes it to within 11 billion miles of SAG-A star without bumping into anything. That puts SAG-A star's 4 million Sun mass into a very small place. For many astrophysicists, this constituted proof that it was indeed a supermassive black hole. But others pointed out that an extremely dense dim star cluster could produce these results. In 2002, S2 made its closest approach to SAG-A star. If SAG-A star were a cluster, S2's orbit would wobble. It did not wobble. This was the final proof point. 1,500 years after Copernicus put the Sun at the center of our solar system, this team identified Sagittarius A star as a supermassive black hole at the center of our galaxy. The gas cloud G2 was first seen in 2002. Observations confirmed that it is on a course for Sag A star. It will have its closest approach to the black hole in mid to late 2013. At this time, the gas cloud will be at a distance of just over 36 light hours from the black hole. If this is the case, a significant amount of it may be sucked into Sag A star. This should lead to a significant brightening of X-ray and other emissions from the black hole that could last for decades. This is the first time ever that the approach of such a doomed cloud to a supermassive black hole has been observed. The black hole at the center of our galaxy is called a supermassive black hole. This kind of black hole usually contains the mass of millions or even billions of suns. The other kind of black hole is the stellar mass black hole. These are created when massive stars reach the ends of their lives and run out of fuel, exploding in super powerful blasts called gamma ray bursts or hypernovas. A typical stellar mass black hole contains the mass of about 10 suns. You'll recall that nova explosions at the end of life for stars less than 5 times the mass of the Sun leave behind a white dwarf. In these stars, electron exclusion pressure is enough to counteract the inward force of gravity. Supernova explosions at the end of life of stars more than 5 times the mass of the Sun leave behind a neutron star. In these stars, electron exclusion pressure is insufficient to overcome the force of gravity, but neutron exclusion pressure is. But if a star is greater than 30 times the mass of the Sun, even neutron exclusion pressure won't do the trick. In fact, there is no known force that will counteract the inward force of gravity for such a supernova or hypernova exploding star. According to Albert Einstein's general theory of relativity, the star will collapse into zero volume and infinite density. This is called a singularity. This defines a black hole. It gets its name from the fact that such a singularity would create a gravitational pull that not even light could escape. The object literally becomes invisible. Carl Schwarzschild, contemporary of Einstein, solved his equation for the special case of a non-rotating sphere. He found that although the diameter of the singularity is 0, the radius at which light would be captured depends entirely on the mass of the black hole. This is called the Schwarzschild radius, and it defines the event horizon. One of the things all rotating black holes have in common, besides the fact that we can't see them, is that matter flows in via an accretion disk. The exact mechanism is not yet fully understood, but we know that gamma ray jets shoot out at the poles, carrying a percentage of the falling matter with it, at speeds approaching the speed of light. Our Milky Way galaxy contains several stellar mass black hole candidates, which are closer to us than the supermassive black hole at the galactic center. This is a low-mass X-ray binary star and black hole candidate. One of the stellar structures in this binary system is known to be a large, dark, compact stellar structure between 3 to 5 times the mass of the Sun, with a diameter of around 25 miles. We calculate this by measuring the motion of gas in the accretion disk and studying the X-ray emission profiles. At a distance of around 3,500 light-years, this is the nearest black hole to Earth. GRO J1655-40, or J1655 for short, is a binary star consisting of an evolving primary star and a massive, unseen companion. They orbit each other every 2.6 days. Based on detailed analysis of star distances, star motions, and neutral hydrogen radiation from spiral arms, we believe that the galaxy is a relatively flat, rotating 100,000 light-year wide disk of some 600 billions of stars. This image, out of the Spitzer Science Center and the University of Wisconsin, represents an attempt to synthesize over a half-century of work on the galactic disk's structure, based on data obtained from the literature at radio, infrared, and visible light wavelengths. The galactic center itself, with the supermassive black hole that we discussed earlier, is shaped like a bar. Although most parts of the Milky Way galaxy are relatively uncrowded, roughly 10 million stars are known to orbit within just a single light year of the galactic center in a region known as the central bulge. Recent surveys discovered the two 3 kiloparsec arms, named for their length. They are now generally thought to be associated with gas flow roughly parallel to the central bar. Using infrared images from Spitzer, scientists have discovered that the Milky Way's elegant spiral structure is dominated by just 2 arms wrapping off the ends of the central bar. One is named Scutum Centaurus, and the other is named Perseus. Each of these major arms consists of billions of young and old stars. 3 thinner arms spiral out between the 2 giant arms. These are called Sagittarius, Norma, and the outer arm. These are primarily filled with gas and pockets of star-forming activity. There is also a spur off the Sagittarius arm called the Orion Spur. It's 3,500 light-years across, 2,000 light-years deep, and approximately 10,000 light-years long. We are located on the inner edge, halfway along this spur, around 26,000 light-years from the galactic center. When we fill the space between the arms, we get the full picture. It's interesting to note that the number of stars per unit volume of space in the region between arms is the same as the number in the arms themselves. What distinguishes the arms is that they have a far greater number of younger stars. In fact, all the known H2 star-forming regions in the galaxy exist inside the arms. We don't see any in the area between the arms. If we lay a grid over the galaxy, we can locate some of the stars, nebula, and H2 regions we have seen in this chapter. Actually, all the local neighborhood stars would fit into the red circle I used to locate our solar system. That would be stars like Wolf 395, Altair, Vega, Polaris, Capella, Aldebaran, the Pleiades, and Betelgeuse. They are all with us in the Orion Spur, as is the Orion, Horsehead, Cone, Witch's Head, Veil, and many other nebula. In Sagittarius, we see the Jewel Box star cluster, and the Trifid, Omega, Lagoon, Eagle, and Cat's Paw nebulas, among others. In Perseus, we see the Rosetta, Heart and Soul nebulas, as well as the Crab supernova, to name just a few. In fact, except for the hypervelocity stars and a few of the supernova remnants, everything we have seen in this chapter is within this red circle. As vast an area as we have covered, it is only a fraction of the Milky Way galaxy. Another point that ought to be covered is that we cannot see through the galactic core into the other side. The core is simply too dense, with stars and gas and dust to penetrate. So this slice of the disk has not been seen or analyzed. But our understanding of spiral galaxies is that they are symmetric. So this picture makes that assumption and fills in the blanks accordingly. Here we see the Sun's orbit around the galactic center. Our orbital speed is approximately 138 miles per second. It takes the solar system about 225 million years to complete one orbit. The last time we were in the same place in our orbit, dinosaurs were just starting to appear on the Earth. We have traveled 1/1000th of a revolution since the origin of humans. Whenever you see a picture of the whole Milky Way, remember that it is an artist's drawing. The size of the galaxy is so large that the distance one must go to see it all is way too far. Here's what I mean. If we assume that our field of view is 140 degrees, we can use trigonometry to find the distance to a point where such a picture could be taken. That point is approximately 186,500 trillion miles from the Sun's current location. Voyager 1 left on its journey in 1975 and is traveling at 38,185 miles per hour. It has already gone 12 billion miles. If we aim it at the photographic point at its current velocity, Voyager won't reach this point for another 558 million years. If some future generation were to ever take such a picture, they would see our entire solar system as little more than a single pixel. At the turn of the 20th century, astronomer Harlow Shapley, studying a large number of RR Lyra stars inside globular clusters, found that the center of the galaxy was far from the Sun. He mapped 93 globular clusters. They formed a spheroidal shape with their own center, not near the Sun. He concluded that these giant clusters formed the bony frame of the galaxy. This area around the disk is called the galactic halo, or corona. It holds a large number of old stars and 158 globular clusters. The galactic halo itself has a diameter of at least 600,000 light years, based on the locations of the globular clusters, although it may extend much further. There is no star formation out in the halo. In 2007, using 20,000 stars observed by the Sloan Digital Sky Survey, an international team of astronomers discovered that the outer Milky Way is a mix of two distinct components rotating in opposite directions. The inner halo, located well outside the disk, rotates in the same direction, but more slowly, at 50,000 miles per hour. In the outer halo, most components spin in the opposite direction, at about 100,000 miles per hour. On September 24, 2012, Chandra found evidence that the Milky Way galaxy is embedded with a large amount of hot gas in the halo. Counting this vast amount of gas, the mass of the halo is estimated to equal the mass of the stars in the galaxy. This has great relevance for the concept of dark matter. The stars in the outer region of the galaxy are orbiting faster than Newton's and Einstein's equations predict. To explain this phenomena, astrophysicists speculate that there must be a large amount of dark matter around the galaxy. They call it dark matter because it does not interact in any way with the matter and electromagnetic energy we see with our instruments. Its only interaction is through gravity. But if these Chandra findings about the hot gas in the halo are confirmed, it could be the solution for star